Okay, so today we'll start a second module. So we have completed analysis of frame. So 2D frame structure, how to analyze by using displacement method. So basically we have discussed two methods. One is slope deflection method and moment distribution method. So we have seen these two methods, how to apply for uh, continuous beams and building frames. So that's what we are discussing last few classes. Today we'll go to the next part of our course. So right now we know how to analyze continuous beam, how to analyze the building frame, which is a rigid jointed portal frame. So how to analyze it? So we can do that. So we have learned that. Okay. So now we'll go to the next topic, that is so analysis of cables and arches. So that is also very similar to the previous cases only. So basically we are discussing uh, indeterminate structures. Okay, so the continuous beam or frames, whatever we are discussing in this course, SA2, they basically all these structures are statically indeterminate. So means we can't analyze by using equations of equilibrium alone. So that is what we are doing. Okay, similar type of structures only we are going to see uh, in this module also. So the structures are different. Instead of frames and beams we have done, so we will move to arches and cables. So at least I think you may have some idea about arches. You may or may not have, uh, but at least you may be knowing what is arches and all the structures you are familiar. So we will see. So this module, it is also like first module was actually very large module. So we have to spend more than 15 class, 17 or 18 class at least. So this module also not very small, but at least minimum we have to spend at least more than 10 class. We have to spend maybe 10 to 15 class, or minimum around 10 class we need. Okay, these are the topics we may be looking at in this module. The two-hinge arch, fixed arches, and suspension cables. Suspension cables mean you may be knowing cable bridges, how to analyze the cables in the suspension bridges. So that is what we are looking at in this module. So all these are basically these are it may be statically indeterminate. Okay, so and so, as a prerequisite. So this topic is required, three hinge arches, but I think you may not be familiar with this. You may not have. I think you did not learn these three hinge arches in SA1. Okay, it's fine. So we'll go from basics. That is why we'll start from basics. So we'll discuss maybe three hinge arches also in between. So this is very simple. So you can do along with this course. Only thing is three hinge arch is not part of the syllabus. SA2 module 2 it is not there. So but you may be, because you have not learned this one completely. I think you can learn along with two hinge arches. Okay, you can learn along with arches and cables, three hinge arches also. So this is going to be very simple because it is a statically determinate. You can say it is statically determinate structure. So we can analyze with the help of equations of equilibrium. So we can do this. So we'll touch this part also a little bit. We discuss about three hinge arches also. Okay, then only I can go for fixed arches and all. Okay, so, but yeah. So I may provide some materials. We can go through that for three hinge arches, but we will discuss along with this. So arches and cables. So both these at least first two or three classes are important because uh, we have an introduction only first two or three, minimum two class or maximum three class. 2 to 3 class we'll have an overall introduction only. Okay. So in that we will discuss arches and cables together because these structures are very similar. So even though it looks different, uh, but these structures are maybe it may the analysis or the force, how the force is transforming, how the force is resisting, or how the load is transferring in these structures. It is very it is in a similar way. Okay, so we'll have an introduction class. At least we'll have common discussion arches and cables. So many times we can compare these two to have a better understanding. Okay. So, so I think you may be knowing what is arches and cables. So whatever the term cables. So I think we had some discussion in introduction class also that time also. So this is what I mean cable. Okay, this is what we are looking at. The cables in a suspension bridge. This is a suspension bridge. So this part. Okay, you can say something like parabola or catenary. So this part is a cable. So this is the main cable in this structure. So we are looking at how to analyze these cable suspended bridges. Okay, these cable means I mean this member only. Okay, so this you may be knowing this because we have discussed already a little bit something about arches and cables in the introduction class. So you just keep in mind this figure. Okay, it is for cables. And arches, you are all familiar already. You know what is arches. So many times we are seeing in either, mostly it will be in bridges or buildings. So may not be in residential building, but many times we can see arches in bridges and all. So I think everybody knows. So just I will show you some later on some photographs and we'll discuss on it. So this is what arches. Okay. So I'm not. So just keep in mind this is these photographs. Okay, these are called arches. Fine. So it could be steel or it could be reinforcement or it could be stone, brick, whatever it is. Okay. So these are known as arches. Okay, let us close it. So okay, okay. So we'll have okay, okay. So let us have some introduction about this. Okay, let us. Okay. So yeah. So this is what this is my cable, right? So this is all. This is a suspension bridge only. This is that. Okay. Wait. Okay. So this one, this black color, no, this is the cable in the bridge, suspension bridge. Okay. Okay. Forget about these bridges and all. So what do you mean by cable? So cable means I'm talking about something like this type of structural member. So what do you mean by cable? So how mainly what type of forces will be there? I think we had some discussion in introduction class. So what is a cable? What is a cable? Somebody can you tell me something?
So the structure which is subjected to tension is known as cable.
Okay, okay. So structural member it is subjected to some tensile force. Okay, so what I mean is internal force will be tensile force in the cable. Okay, I think you mean that. Okay, that is correct. So, but then what is the difference between tie member of a truss and cable? Because tie member, this may be knowing. So, whenever you are analyzing trusses, you will end up with two types of forces. Some members will have some compressive force, and some members will have some tensile force. So, the members which are carrying a compressive force, what name you will call? What is the name for that type of members? Can you tell me what is the if you have a truss member, some members will have compression force, some members will be experiencing tensile force. So what you will call the compression member of a truss? What is that terminology? Compression member of a truss.
So strut.
Yeah, strut. So similarly, you will be calling the tension member of a truss. You can call it as tie. So that is also purely only tension. That what will be the difference? What is the difference between tie and a cable? So both are tension members. So then how will you differentiate a tie between a tie member and a cable? How can you differentiate? You can tell whatever you are thinking. Whatever you are telling, it is correct. Okay, don't worry. So what is the difference between tie and a cable? What is the difference? So what will be the difference? You can say this is a cable and it is a truss member. Or this maybe you can say if it is a truss or the configuration, these bottom cord members will be under tension force and these green color members will be in compression force. So the difference between tie and a cable. So what will be the difference?
So the tie is a member which is connecting to tension member in a truss.
Okay,
But cable,
cable, yeah. Okay, fine. So the difference is we can see that if you, so I will show you some photographs later on. Or you have seen already in that introduction class, we had a bridge and we had a bridge and we had cable, something parabolic. Okay, we had this is the cable. It is also experiencing purely tensile force only. So we will see that how it is only tensile force coming. All those we are going to discuss in detail. So the main difference is when you look at the cable, that member is very flexible. Because if you change the loading, or if you it is like you can say it is something like a rope. If you keep rope at two ends, you just fix it, and if you keep some weight, it will you may see that it will change its profile. Something like it may sag or something like this. Okay, so the cable is the main difference is both are tension members only, but cable is that is very flexible. The member is very flexible. So it will be like you can see the cable, it is very flexible. You must have seen at least in some bridges this cable, we can see that cable is very flexible, but the truss members are not flexible. That is kind of it's a rigid member only. Because this is some steel or steel member or wooden member, whatever it is not flexible. It is not flexible like a cable. The cable basically you can say it is something like a spring. It is a steel wire or something. You can say that is very flexible. So that is the difference between cable and a tie member. The cable is more flexible, and but the tie member is not like that. That is having some stiffness. So this truss structure cannot be flexible. If it is flexible, it can't take any load. It is not flexible, but cable means it is flexible. So now can you tell me what do you mean by flexible? So what do you mean by flexible? These terms you may be familiar. So what do you mean by flexible? We have discussed in beam also. What do you mean by
So
flexible?
the member
Uh,
which is stretchable.
yes, okay. Yeah, it is stretchable. So you can say that more precisely. The flexible means, yes, the flexure rigidity, you can say that it is zero. Ideally, you can say that in an ideal case, we must have discussed in beam also. The EI, if you say with respect to beam, if you're talking about stiffness or flexibility, you will be looking at EI value, the flexure rigidity. So that is, if that is if member is completely flexible, means we can say that flexure rigidity is theoretically zero. If flexure rigidity will be zero, that is the meaning of flexibility. That is the meaning of the member is flexible. The cable is flexible, so we can say that flexibility it will be zero. And so the string or cable, whatever it is, actually it can't take any. It cannot bend actually. It cannot bend like a beam. Suppose if you have a beam, so if you have a beam, let us take. Okay, so suppose if you have a beam, and if you apply some load, it will transfer the load by bending action. It will bend, and then it will transfer the force to the support or columns, whatever it is. That is why the bending moment and shear force are coming into the picture when you are analyzing a beam. But the cable or string, it can't bend. Okay, because it has no pressure rigidity, so it can't bend. So you can't use like this. If you keep a cable and if you apply some load, it will keep on deforming. It will keep on changing its profile. Okay, so that's why you can say that string or cable, it can't bend. Um, so you can say that stiffness. Okay, its stiffness is practically going to be zero. The cables, the stiffness is practically going to be zero. There is no stiffness for the cable. Okay, because usually the cables and all, we'll discuss these all things. Okay, usually the cables and all, there is unless it is very large diameter, then only it is having some stiffness. But otherwise, the stiffness is going to be uh, zero. Okay, so yeah, so the cable also it can't take any compressive force also. If you have a cable, if you apply some compressive force, it cannot resist that force also. Can take only the tensile force. That is why we are using for a specific purpose only, in especially widely used for bridges. Either it may be suspension bridge, something like this, or cable stayed bridge. Also, we are using that cable. Okay, so because there only tensile force will be coming, so that force it can transfer very effectively. That is why you can see that very large span bridges. So that will be made of suspension. That will be mostly either suspension bridge or cable stayed bridge, because we can go for larger span. Those things we can discuss later. So if you are going for a simple continuous beam, that type of construction, that will be very uneconomical. The size of structure itself will be very huge if you are going for large span. Okay, so, but you can easily go for large span bridges with the help of cables. Okay, so that is the main difference between a tie member and a cable. So both are tension force, both are experiencing only tensile force, but that is, how to differentiate or distinguish between these two, we can say that in terms of stiffness or flexural flexibility. The cables are very flexible structural members, and but the tie member is just a rigid bar. It is not it is not flexible as in case of cable. Okay, but both are experiencing only tensile force. And again, in truss, it can also take compressive force, but cable can take only tensile force. It can't take any bending, or it can't take any compressive force. Okay, so we'll see all those things in detail. So we will have a brief introduction only. Okay, the next. So what is the difference between cable and arch? What is the difference between cable and arch? So because we have seen some photos, cables and arches, at least in look wise, how what is the difference? Shape wise, or what is the difference between cables and arch? Or how, or what something is common also between them? How okay, can you tell me what is the difference between cable and arch?
Sir, cables are subjected
Cable is
to.
inverted arch.
Okay, yeah, that is, yeah, okay, that is good. Yeah, if you look at the structure, we can say that uh, you can make to okay. So you can say that by look wise, or by how you can say that suppose mostly it may be, suppose if you take a parabolic arch, a cable also it looks parabola shape only, but so one is, we can say the cable, you can say that it is an inverted arch. Okay, it is an that is a look wise we can say, by looking at the structure you can say the inverted arch. So inverted, yeah, cable is an inverted arch. It will look like something like that, right? So I think
So the main difference is
uh,
cables are subjected to tension while arches are subjected to compression.
yeah, okay, yeah, very good. So yeah, that is also very precise answer. So this is an arch, it will look like this. So cables will look something like this. So we can say that by appearance it is an inverted arch, you can call. But the load transfer, if you see the internal forces, the cable is going to experience purely tensile force, but arch going to resist the load primarily through axial compression. Okay, axial compression. Okay, so in okay, we'll discuss. So arches resist load through axial compression, and cable resist the load through axial tension. Okay, that is a difference when you come to the load transfer mechanism. This is a difference. So now we can say something is common also. So what is the common? Mainly between arches and cables, both of these structural elements, or both of these structures are going to transfer the load, or load transfer mechanism is mainly through axial force. The internal force will be mainly axial force. It may be compressive force in arches, and in cable it will be mainly axial tension force. So we will see all those things. So how, why it is only axial compressive force, we will discuss those things, okay, in detail. No need to worry. But just because okay, this is the difference, or this is the common thing, you can say that both are having some both internal force will be primarily axial force. Okay, compressive force in arches, and tensile force in cable. Okay, so internal force in arch is yeah, so it is rarely pure compression. In the real arch, let us say, why it is compression. Suppose if you take an arch, it will be something like this. Okay, so it is an arch, simple line diagram I am given. So what will be the loading? The loading will be something like this, right? This is the loading. So once you apply this loading, okay, you take a beam also. Let us for the comparison, you take a beam first, apply this load, it will bend. Okay, it will bend, and so some of the fibers, maybe above neutral axis, it will be having some compressive force, and below neutral axis it will be having some tensile force. It is in the case of a beam. Okay, but for arch, so the tensile force, it can experience tensile force, but mainly only compressive force will be there, because it's something like a hog. You can say that the shape will be hogging, right? So to have some tensile force, we have to apply some more load. So once some hogging moment comes, then only the tensile force will be coming in the arch. Because of its shape, it is already having some right. This is called rise in the arch. Because of this rise, the arches mainly only compressive force will be there. Okay, but in the real structure, if you take a real arch, if you take a real structure, very rarely will come across this condition. Pure compression may not be the in practical pure compression may not be the case, but there may be internal bending moment and shear force also. But obviously that will be very less. Moment and shear force will be very less compared to the same beam. Same if you take the same span beam, you apply the same loading, but this beam will have more moment and shear force. But definitely the arches will have very less amount of moment and shear force. Primarily, it is carrying a load by axial compression. So here also you can see carefully what is the difference. Arches primarily compressive force, but moment and shear force is possible. But whereas in cables, it is always in pure tension because it is flexible and it can't bend. It cannot resist any moment or shear force. That is why in cables always will have pure tension, but in arches. So either we can have arch with only compressive force or compressive stress, and also in the real arch it can also have some moment and shear force. Because arch is a you can say cable is a flexible structure, but arch is it a flexible? No, it is a rigid because arch is made of it may be some masonry or concrete or brick. So it is a rigid structure. It is not so whereas in cable it is flexible, and if you apply some load only one if you apply only one point load, it may take something like this type of shape, a linear shape. But if you apply some uniform load like this, it may take the shape is something different. It may be look parabolic shape because it is flexible. It will keep on change the shape, the cable structure. But arch is a rigid structure because it is made of some masonry, either brick, concrete, or steel, whatever it is. So once you cast the arch, whatever the load you're applying, it doesn't matter. It won't change the shape. The shape will be constant. How we are cast the structure, it will remain in that shape only. Okay, but because of its shape only, because of this shape only, the mainly arch is carrying the load by axial compression. But in cable it is uh, purely tensile force only. Okay, so we have seen this. Practically, internal force in arch is like a plane frame element. So this is an arch. So this one you can take. It is same as plane frame. So we have discussed all these type of uh, structure, plane frame structure. In we have seen how to analyze it. But arch also same thing. It is not different from this plane frame structure. Arch is like a plane frame element only. Only thing is generally once you say arch mean will our mind will have this type of uh, picture. It is something like a semicircular or curved geometry. That is called arch. But frame means it will be something like a building frame, orthogonal frame, beam and column. But these two both are coming under same category of structure. The arch is some arch. The practically the force in arch, internal force in arch, it is like a plane frame element. And if you have a plane frame element, generally how many force internal force component will be there? If you take a section, if you take a cut, there will be some bending moment, some shear force, and some axial force. So there will be three internal forces. But that is what this sentence practically internal force in arch is like a plane frame element. Always there will be some shear force, some bending moment, and some axial force, except some special case. So because here we have discussed arches, so we can also make an arch. Uh, uh, Arch that is going to experience only compressive force. That is also possible. That is why I have written here except some special cases. Except some special cases, internal force components in arches also there will be three internal force components. We can treat it is like a plane frame structure only. So there will be moment, shear force, and axial forces in general. But in some special, except some special case, I think we will discuss this. What are those special cases? So I think yeah, you can see this is the arch. You can see it is going to experience only compressive force. So we will see all those things. In the numerical example, we will find that moment and all will be less. That is why it is going to experience only compressive force. That is mainly coming because of this shape. Okay, because of this shape only. So already it is having some hogging. That is the shape. So it won't moment won't come actually. The moment will be very less. How it is, I think we will discuss in detail. Okay. Yeah, so what are those special cases? The special case in the sense, in some cases, we may not have moment, we may not have much bending moment and shear force in arches. So let us discuss Let us discuss those things. Okay. Okay. So okay. So they are called some special cases, or they are called the term the funicular structures. Okay. So if you did not learn 3-hinge arches, so may not be familiar with this term. So that is why we will discuss in detail. Okay, what do you mean by funicular structures? Okay, so the special cases means what I mean is, so we can have an arch which is going to have only axial force, only compressive force. There is no moment and shift. So those type of arches or those type of structures we can call it as funicular structures. And cables are always funicular. Actually, the term funicular, this means it is coming from spring. This word is coming from string or cable. The meaning is, so the cables or string means it is flexible, so it can't bend, or it cannot take any it can't bend. It can take only axial tensile force. The term funicular means that type of structural system will be called funicular. So only axial force will be there as an internal force. So cables are always funicular. They want it because it can't bend, cannot take any moment or shear force. That is why there will be only axial tensile force. But arches also can be arches also can be coming under that category. Like only axial compressive force is possible. Okay, we'll discuss that. Cables means why it is. Okay, we'll see this. Cables actually, if you apply some load, what will happen is cable will keep on changing its shape according to the load, whatever load you're applying. So means like this. Suppose if you have a simple example, you can say that suppose you have a rope or something. We used to have like to keep some clothes. No, suppose uh, you have a rope to keep some clothes in sunlight. So what do you do? Suppose if you keep some weight at the middle, or if you keep some shirt or something at the middle, so this rope may take shape something like this. It may have this type of profile. So if you are keeping only weight at the middle, you may not see this much space. But suppose if you keep a shirt in that rope, or if you keep some weight, it will take this shape. But if you take the same cable or same rope, and if you keep some weight distributed, so if you keep some weight distributed like this, so either you keep so many shirt, or so many weight you keep continuously along the length, so that you can take it as an distributed load, UDL. You can take it as UDL. If you keep the load like this, what will happen to this cable? Same cable I am talking about. So here it will have a linear profile, something like a triangle. So but here this cable will, or cable or rope, because both I can take it as same, because rope also, if you have a rope, it can take only tensile force. If you pull it, it will resist to some extent. If you apply some compressive force, there is no resistance at all. Okay, you can't apply any bending load or something. Okay, but so if you apply distributed load, what will happen to that rope? Or you keep clothes, so many clothes, maybe you put some saree or something, keep like this entire length. What will happen? It may look something like a parabolic shape. So that is what happening in the real structure also. Cable means the cable, you can take it as, you can say that it keep on changing its shape depends upon the load. Okay, because it is flexible. Practically the flexibility is zero, uh, the stiffness is zero, so you can take it as, so because of this, it can't take any bending or moment, so only there will be axial force. So such system will be called a funicular structure or funicular system. The simple meaning, we'll discuss all, we'll derive also the conditions and all. Mathematically also I'll prove it. But for the time being, you understand this term, the funicular structures or funicular system. That means the system which is having only axial force. There is no moment, there is no shear force, there is no maybe twisting moment, etc. There is only, it is resisting the load purely by compression or purely by tension. Such systems are calling funicular structures. Actually, the word funicular, it is coming from string or cable only. Later on, we expanded that to arches also, um, with respect to the compressive force. Okay, the arch is funicular. So when it will have arch is funicular, if that is the case, it will have pure compression only for for a particular type of load. So ideally we have to consider which is the most predominant loads. Okay. Yeah. So the thing is, the main point is we will see all those things. Mathematically, I will prove it. But for the time being, you understand the cable is always funicular, always tensile force. Why? Because it is keep on changing the shape. Once you apply the load, it will change the shape. So finally, only internal force will be only moment, only tension force will be coming. But which is not possible in arches because arch is a rigid structure made of some masonry. It is a rigid structure. It cannot take, it can't change the shape. Once you cast some semicircular arch, that will be semicircular. Or if you cast a parabolic arch, if you're applying point load, uniformly distributed load, or any other type of loading, doesn't matter. Arch will be always in that shape, parabolic shape, if you cast in that shape. Okay. So, so suppose, but if you make a if you take some particular type of loading, let us say UDL, and if you design a arch, you can design an arch for that set of loading to get this condition. Particular system means we can for a one type of one set of loading, you can design your arch, you can get a profile. It may be linear arch or it may be parabolic or semicircular, whatever it is. You can design a configuration of the arch. So that will be a funicular arch for that type of loading. If you change the loading, then there will be some moment and shear force will be coming. Okay, so that is why arch is funicular. That is a special case only for some particular type of loading. But cables won't be like that. Cable will be always, it will be funicular because it will keep on changing. Depends on the load you are applying. So that is a difference. So here, what you have to remember at this point of time, at least you just understand what is mean by funicular structures or funicular systems. The meaning is simple. It is resisting the load only through axial forces. It may be compression, then you will be calling funicular arch, is that type of arch. Only compressive force is there, and cables are always funicular. There is always only tensile force will be there. Okay, so we'll discuss and cables. Yeah, cables not need to worry. Whatever is the load you're applying, it will keep on change its shape, so that it will be always uh, funicular structure. Okay, so arch is rigid and not changing shape is possible, but cable unite is flexible, so it will the shape it can change. Okay. So some of the examples or applications of cables. So it could be you can use it for in suspension bridges. So we'll see this. I will show you some good photographs and I will explain its components and all later on. So but let us have some. This is a bridge. Okay, it is a bridge and this is a deck. This is a deck, bridge deck you can say. So maybe the traffic may be passing over this deck. So the bridge could be uh, what you will call it. It is a pedestrian bridge or it can pass vehicles, whatever it is. Okay, so both type of bridges are you can find lot of bridges that is suspension bridges. Okay, so this one it can be a pedestrian bridge or it can be a traffic. It can take vehicle load also. So whatever it is, this part will be called in deck, and deck will be this is the cable. This is the parabolic cable. That is the main cable. Okay, this is the main cable in the bridge. So how the deck is supported? In this case, you can see some vertical element. These vertical elements, so that is known as hangers or suspenders. This is, so I will be writing, this is known as the vertical elements, the hangers or suspenders. Okay, the closely spaced vertical elements called hangers or suspenders. So they are actually they are also in under what type of force? Always in tensile force. So they are actually transferring the load, deck load, weight of the deck, weight of the vehicles, weight of the people who are working over this deck. All these weights are all these loads are transforming. All these loads are transfer from the deck to the main cables through these hangers or suspenders. So this one also made of steel wire only, like cables. These are also cables only, vertical. You can say these are also steel only. But the entire load from the deck is transferred. It is transferring from the deck to the main cable through these vertical elements. So these are known as hangers or suspenders. Okay, so this is how the load is transferring. Whatever the load coming to this deck, everything is taking this main cable. Okay, finally this cable is this is known as anchoring. So this is known as anchoring. So finally these cables are anchored to the ground somewhere here. So here we'll be having foundation. Okay, so here the load is transferring, actually all the weight we are applying, load we are applying into the deck, the weight of the vehicles, etc. And everything is transferring through this vertical members to the uh, main cables. This is the suspension cables we are talking about. Okay, so then finally these cables will be anchored to the ground at the two ends. So then we'll be having foundations and all. So that is how the load transfer in the suspension bridges. So if you say the cable stayed bridges, so it will be something like this. So this is known as the cables, main cables. So this will be always under tensile force. Here also these hangers as well as the suspension, this cable, always it will be in some tensile force only. Okay. So we'll see that how to analyze this type. And another one could be cable car. Some of you must have uh, use this cable car, so we can, so it is also a very good example of suspension cable. It is a cable. So here this is the cables, and this is moving from one end to another end. So it can move from one end to another end like that. Okay. So it is some kind of roof system. So it is also like a cantilever system. So all these are connected to this vertical members through cable. So this cable also always under tensile force. These are some examples where we have cables, and always these cables are only experiencing only tensile force. So that's why we are calling it, these are known as funicular systems. So we'll discuss this one in detail, how it is coming, how it is. Okay. So if you come to the assumptions of cables, while analyzing the cables, we used to have two assumptions mainly. So whatever analysis we are doing, first we used to see the assumptions in that analysis. If we are discussing about bending theory of beam, so we have some set of assumptions. Okay, so without assumption there is no theory. So here two assumptions mainly we have to make. We have already discussed. The first one is we'll make an assumption. The cable is perfectly flexible. Perfectly flexible. What does it mean? The meaning is it can't take any shear force, bending moment, or axial compression. It can take only axial tension. That is the first assumption we used to make. Okay. And second assumption, the cable is inextensible. This is an extra. So this assumption is cable is inextensible. So here the change in the change in length is negligible. So because you have a cable part of a bridge, and it is having some tensile force, but we will not consider that um, extension that is going to happen in that cable. It is experiencing tensile force, but we will take in uh, the structure analysis. What you will take is we'll assume cable is inextensible. So with these two assumptions only we are going to analyze the cable. Okay, so the first assumption is perfectly flexible. Uh, Practically the stiffness is zero, you can say. And second assumption is cable is inextensible. Change in length is negligibly small. Okay, these are the two assumptions we used to have. Okay. So now we'll understand that funicular system. So that part is not, now you may be knowing only definitions. The funicular system is only it is going to have axial force. Maybe there is no moment, or there is no shear force, moment and bending moment and shear force. Okay, so that we will understand. I think I will give an example. So I'll give an example. Then we'll start. Okay, this will be, so simple one is let us take a truss. Okay, let us take a truss. So this is a truss. So I am taking this hinge support. This is a pin joint. Let us take it is a joint. It's pin joint. Okay, so I am applying some load. So here with this we'll discuss. I think I will try to explain in little bit more detail the funicular system. Then we will go to the arches. Okay. So let us take a truss. So I am applying some load P. So I am applying some load P. Okay, let us take this is, So this is the load point. So let us take somewhere here. So this length is A and this length is 4A, right? This length is A, this length is 4A. Okay, this point I'm calling A, B, C, right? A, B, C. So let us take this height is, this height is 3 times A. Okay, so yeah. So in this, it is a truss. It is a frame. It is a framing. It is a. I'm calling it is truss because I have taken this joint, this pin joint. Joint is pin joint. So that means this frame is you can call it as a truss. Of course, you can call it as a truss. So what is the reaction? Can you tell me what is the vertical reaction at A and C? Vertical reaction at A and C. What will be the vertical reaction? So in this case, what will be the vertical reaction? So we can use the equilibrium equations. RA plus if you write VA vertical reaction VA plus VC, that is equal to P, and VA and VC will be, what will be the proportion of VA and VC? You may be knowing this simple case. No need to use any equations. So we have a load W and this is A, this is B. What will be this reaction? What will be this reaction? So what will be this reaction? Anybody?
WA by A plus B.
W.
W WB by A plus B.
Okay. So W.
WA by A plus B.
Yeah. So it means you can very simple. You look at this beam, simply supported beam. So this load is dividing your span in the, what is the proportion? A is to B, right? A is to B, and L is the length of the beam. So this load is dividing the span A is to B, that ratio. So if you look at the reaction value also will have same proportion. It used to have, it is a WB by L, it is a WA by L. If you take the reaction ratio, you will find same ratio. So only thing is this will be having WB by L, this will be WA by L. It is also, the reaction also will be in the same proportion B by A. Okay, just reverse because this load is closer to this point, so this support will be having larger value, but proportion will be A is to B or B is to A, you can say. So that means this will be how, what is this reaction? That is going to be P P. Okay, so this one will be P4A by 5A, right? That is the reaction. So 4P by 5. Okay, the total symbol. So see, this is dividing this load a 1 is to 4 ratio. So the reaction value also will be in the 1 is to 4 ratio. The 1 is to 4 means the 4 will be coming at this point, and this will be having only, the ratio will be the reaction will be just P by 5. Okay. So if you have doubt, you can use the equilibrium equation. You can get this reaction value. So this will be 4P by 5. This will be P by 5. You can directly write this. Okay, you can directly write this value by looking at this proportion 1 is to 4. So 1 is to 4 ratio. Okay. So this is the vertical reaction. How will you find the horizontal reaction at this point? Because these are hinge support, there will be some horizontal reaction, right, at A and C, or it will be 0. There will be some horizontal reaction because you can see, you take this truss, you assume it is roller. So anybody, can you tell me what is the direction of this reaction HA and HC? Towards right or towards HA? What is the direction of HA? Can anybody guess what will be the direction?
HA left side, HB right side.
So HA will be towards right, left or right?
Reaction will be towards right side. HA.
HA will be towards right. Yes, correct. The simple understand, you take this truss, you keep both support and roller support. If you apply the load, what will be the tendency at this joint? It will have a tendency to move in this which direction?
Left.
It will try
Joint
to
left.
it will try to move this direction, and this joint will try to move this direction. So we are arresting that movement. So that is why we are going to have some reaction. It is in the opposite direction. Okay, so that means we will be having some reaction towards right, and here we will be having some horizontal reaction towards left. So how will you get this value? How will you get this value? This is a pin joint. How will you get this value? Tell me fast. How will you get this value? Means you just give me the step. I don't want the value. I will give the value. How will you solve this reaction? How will you find out this reaction value?
Moment at B is equals to
Yeah,
0.
if it's a pin joint, you can take the moment about B and you solve that the reaction into A minus this reaction into H into this height. Okay, once you solve it, you will get this is 4p by 5, 4p by 15. Okay, and what will be this reaction? It will be equal because there is no other horizontal load. So whatever this reaction, so this must be equal to this reaction. So this will be 4p by 15. 4p by 15.
Sir, directly we can use components.
Whatever it is, you can get this value. Okay, fine. So this is how the reaction you can get vertical reaction, horizontal reaction. So but these two will be just equal and opposite to satisfy the horizontal equilibrium equation. Okay, so let us if you draw the free body diagram for these two members, this is your AB and it is your BC. Okay, so this will be like this. I have some horizontal reaction, I have some vertical reaction. So that this if you separate at the joint B, so here will be having this is the horizontal force, internal force, and here will be having something like this. Okay, so this is the two force I have. Maybe you can say that the resultant will be there, something like this. The resultant of these two forces will be acting along this member. Resultant of these two will be acting along this member. So means this member is under compressive force. Some force under compression. Some compressive force is acting along this member. Similarly, this member, what is the free body diagram? Here will be having horizontal reaction, here will be having vertical reaction, and here we'll have just opposite, and this is the second member. This member also in compression. Okay, so we have solved this. Okay, so now I will take the same frame. So I'm going to make it. I'm going to make one changes. I'm going to make this joint as pin joint. Sorry, the rigid joint. So I'm going to take the same frame. Okay, so I'm going to keep the same support. Both supports are hinged, and this length is I'm taking A. This length is I'm taking 4A. So I'm applying same load P at joint B. So here the joint B is a rigid joint. So here the joint B is a rigid joint. Okay, so now you tell me. So I think you got this. You have analyzed this stress completely. You got all these reactions and all. So you got the reaction. You can find out the compressive force if you want. You can take the resultant of these two forces. You can get the compressive force. So I think you understood this completely. Now you tell me what is the difference? What will be the difference? If now joint B is a rigid joint, so will there be any difference at the reaction value at joint A and C? Vertical reaction will it have any difference? So what
No, sir.
it will be same. There won't be any difference at all. 4p by 5. So the span is dividing in the ratio 1:4. The reaction also 1:4. So this is p by 5. Okay, so vertical reaction will be remain same, but here can you find out the support reaction, horizontal reaction? Here also we'll have some. Here
Horizontal zeros.
horizontal reaction, how it will be 0? Again,
The rigid point.
this is rigid, but again you can apply the same logic. If you keep it roller, it will try to move away, it will try to expand. So by keeping the hinge, so we are resisting that movement. So the reaction will be there towards right, here will be towards left. The reaction will be there, only point is here some reaction will be there, maybe x, this one also will be x. But can you find out this value x at this stage? Can you find out the value of reaction in this rigid jointed frame? Can you find out this value directly by using equilibrium equations? No, because
No.
because the moment at B that condition is not available. Here we could use sigma mb which is equal to 0 because it is a pin joint, so we can use this condition. We can find out the support reaction. Both reaction will be just equal and opposite. But that is not available because here the joint B is the rigid joint, so that equation is not available. Okay. Okay, but so what is the difference? Here the joint B, this is a rigid joint, that means there will be some moment, right? There will be some moment here and there will be some moment here, equal and opposite. Because I think you may be remembering this, we have done this type of questions, frame. apply some point load. What is the moment diagram for this case? Moment diagram, it will be something like this. So here we may have some anticlockwise moment, and this is my free moment diagram, and here we'll be having clockwise. So it may be something like this, right? That means here I will be having some anti-clockwise. If it's anti-clockwise, this must be clockwise. Okay. So I think it is the same thing here also. Here we may have some clockwise. So here we should have some anti-clockwise. Because it is the rigid joint, the moment will not be zero. Moment will be there, but equal and opposite. Two members will be there will be some moment will be there at the two members at that joint. Okay. But in this case, the pin joint means moment at B. There won't be any moment. Moment will be zero. It is just free to rotate, but that is not the case with this frame. Okay, so now I have a question like what will be the here will be having some moment something like this because it is a rigid joint. So what will be the direction of moment, sagging or hogging here? AB here with what is the direction, sagging or hogging? So that also we can't tell actually. So let us take if it is sagging moment like this anti-clockwise, then what should be the moment at this member and in this member? If it is anti-clockwise, it should be which direction? By keeping this in mind,
Right.
it should be like this clockwise. Okay, that is the one possibility because we don't know about the direction. And another case I am giving, suppose if somebody is taking, if it is, let us say if it is clockwise, if it is clockwise, this must be anti-clockwise, right? That is the condition. This is the joint. So if it is clockwise, there should be anti-clockwise moment, equal magnitude. Okay, that is the one point with respect to moment direction. Okay, so now my another question is, can you draw the deformed shape? Can you draw the deformed shape for this frame? The deformed shape by keeping that compatibility condition. What is a deformed? What is the condition while drawing the deformed shape for a frame at the rigid joint? What should be the condition? If it is a sagging moment, how it will deform? It will deform something like this, right? Then what is the condition? How this member should deform? It should deform like sagging or it should deform hogging? By keeping the compatibility condition. What do you mean? What do you mean by compatibility condition? Compatibility condition, that means at the rigid joint, even after the deformation, what should maintain? What is that? Yeah, angle 90 degree, not 90 degree. Whatever is the angle, whatever is the initial angle, it should maintain. So this could be 90 or it may be more than 90. Whatever it is, the initial angle, it should maintain. Okay, that is the compatibility condition at the rigid joint. So we have to maintain that condition while drawing the deformed shape. Okay, so now you tell me if it is sagging moment. So what is this moment for this member? Can you tell me what is this moment? Sagging or
Okay.
Hogging.
no? For this member BC, what is this moment? Why it is sagging?
Sagging.
It is also sagging, right? As per this is anti-clockwise, it is clockwise. So it is sagging this member, it is also sagging as per this, right? How we are saying AB sagging, so we are looking from inside. Same way you look at this member, what is this moment? It is also sagging. So it is anti-clockwise, it should be clockwise. Why? Because of this condition. That is the first part. Let us leave that moment part. Okay, by keeping this condition. Okay. So now you come to the deformed shape. Huh?
Sir, but it is not maintaining.
Okay. So there is some mismatch. Okay, let us forget about this moment direction. Now you tell me if if you take this moment sagging, and if this member is having sagging moment, it will deform like this. To maintain this angle, what should be the deform? It should deform like this or it should deform like this? First one or second one? How it should go?
Second one.
Yeah, it should go at this member. It should be like this, right? So then deform shape is correct, but it is not matching with this moment, right? Same way, if you draw the deformed shape for this second case, it is second possibility. I have taken this member AB normally hogging. And if it is hogging, it is also coming hogging to keep this condition. But let us draw the deformed shape again for this case. Okay, so this is my frame and this is my second member. So the deformed shape is, so this is hogging, so I am drawing this is, it may deform like this. So to keep angle remain same, okay, it is not always 90, whatever is angle, we have to maintain that angle, only that's the condition. Generally orthogonal frame is, it will be 90 always. Okay, that is why the definition we used to say rigid joint means it will maintain the 90 degree. Okay. But this, if it is 100 degree, it should maintain 100 degree. That is the meaning. The rigid, so it has to go like this only. Okay. So that means now we have a mismatch. Both these are not matching. For moment directions and deformed shape are not matching. So then finally, how the member should deform? What is the final conclusion? This is the first case, it is second case. But we found that both are not possible. It is also not possible, it is also not possible. If there is a moment, these two both are not possible because it has to maintain the compatibility condition if it is the joint, and also it has to maintain the moment at equilibrium also. Finally, what will be the conclusion? How it will deform? Should this member sag or it should hog? And if it is sagging, it is also should sag as per this, but it is going opposite. Okay, so from here, what is the time? 46. Okay, okay, I have to wind up. Okay, let us take 2 minutes. From here, I can say that finally, in this case, actually the members are going to get confused because this is sagging, it has to sag, but as per the compatibility condition, it is coming hogging. If it is hogging, this member also should hog, but compatibility condition, as per the compatibility condition, it is sagging. That means you can say that members are getting confused in this case because of this profile. That case we will discuss why it is. We will discuss in next class. But here, finally, and 1 and 2 both these deformations are not possible. Finally, what happens is it will just remain as it is, like this is a case, and after applying the load also there won't be any sagging or hogging, nothing will be there in these two members, so this member will remains as it is. Okay. This is actually because this shape is you can say it is a I call it a frame. It is a frame, so it is not a truss. It is a frame, the rigid jointed frame, 2D frame. So you can also call it as a linear arch. It is simply arch only. It is a arch or frame, both are same. Okay, only thing is it is a linear arch. It is not circular or parabolic. It is a simply linear arch. So this here there is no sagging or hogging in these two members, means there is no bending at all. And that is actually happening because this shape, the shape of this, the structure is, the shape is uh, simply funicular shape. That is why the moment is completely getting eliminated. Okay. The geometry. So why? Because I think we will discuss tomorrow. That is what happened here actually. Actually, that happened because the shape itself is a funicular shape. That is why the moment is not coming. Even though this joint is a rigid joint, it is acting something like a pin joint. So finally, the moment at B. So moment at this joint, okay, that will be equal to 0. There won't be any moment at all in this case. So in this case, because the shape is a funicular shape, that is why our the rigid joint also acting as a pin joint. Okay, so we'll discuss this one from here. Why it is funicular, we'll go further discussion tomorrow. Okay, but that is the reason. Even though if you have a funicular shape, your frame will behave like a. Even though you have some the rigid joints, so you will find that not only at this joint, you will find that at each and every point in this structure there won't be any moment at all. It will completely get eliminated. That is because of this funicular shape. Okay, so I think I will stop here. So we will continue from here. Okay, tomorrow. Once you complete the complete discussion, then you will understand completely. Okay. So, but here I did not derive it, but I have proved the moment is going to be 0, there won't be any bending because of this. Because these members are getting confused whether it should sag or it hog. Finally, the confusion has been eliminated by remains as it is. There is no deformation at all. Finally, the rigid joint is also behave it like a pin joint. So that is the final conclusion. That happens because of the geometry is funicular. The structure shape is funicular. That is the reason. So we'll discuss it tomorrow in detail, remind things. Okay. So I think everybody must have filled the attendance form. You can leave.